hard to follow.
That's right. Waste of time.
I mean, isn't that actually the definition?
Wait. Which time? You said waste of time.
The
Which time?
mathematical convolution.
Oh, okay.
Second time.
But why? Can I ask why it gets that name? I mean, it isn't like convoluted. It's convoluted. But I mean, like, why
I
do they call it?
don't know. So I don't know the etymology
Okay.
of that.
I mean, it's suiting.
Well,
And I don't know which came first, convolution or convolution.
well, isn't to convolute to change?
So, like, I don't know if sort of the mathematical definition of convolution came about, and then people were like, well, that's just a mess. So that's convoluted, right?
Okay, that's fair. Sorry, I know it's not related to the class. I was just curious.
Well, it is related. It helps. Sometimes it helps understand context, right? When you understand that median and mediocre actually are derived from a Latin word meaning halfway up a mountain, right? That, I don't know, helps. Anyway, back to convolution. What is convolution? What is it? What does it mean?
It's really solving a problem by changing the form of mathematical expressions from derivatives to something you can actually solve.
No. Okay, so it's a convolution integral.
Function derived from given function by
Okay. So in the context of signals and systems, right? We have spent a couple of days talking about convolution. We're going to spend the third day talking about convolution. And it has been oh so much fun. Why are we talking about convolution?
It's useful
because we want to tear a signal apart, analyze a signal, or send it through a process, and then put it back together.
Okay.
Put it through a system.
So we're gonna tear a signal apart. What are we tearing signals apart into? Impulses. So we're tearing signals apart into impulses. And then we put each impulse through a process. We put each impulse into the system. And then we're able to combine the results. That's fundamentally what we're doing. And when we sort of looked at those three blocks, we were able to sum those three blocks. But then as we thought about, what happens as we move from just these blocks to sort of continuous things, we realized that we moved from a summation to an integration, right? And I think we even did that, didn't we?
Yeah.
I think maybe we should do another one. So let's consider the following. Let's say that I have a system.
So 1 foot in from each of those aluminum.
So like here to about here.
Perfect.
Okay, I'll try. I make no promises. So lost you totally.
Sorry.
My train of thought. Give me a moment to recompose myself. Okay, so let us say that I have a system F. No, not F. G, and when I put in an impulse into this system, I get out a triangle. So the impulse response, h of t, mathematically is going to equal 0 for t less than 0. It will equal 1 minus t for 0 to 1, and it will equal 0 for t greater than 1. What questions do you have about this?
So it makes that a 45, right?
Yes.
Okay.
Right? I mean, although I can say that this is one horizontal unit, this is one time unit, right? I mean, this, my vertical axis could be in force, and my horizontal axis could be in time. All right. So that's my impulse response. What does that mean? Tell me what that means in English. What does impulse response mean in English?
Reaction.
Reaction. Reaction to what? To an impulse. This is how my system responds if I dump energy into it, 1 unit of energy into it instantaneously. All right, so now I'm going to put in some energy into my system. And I'm going to put the following in. I will put in x of t equals 0 for t less than 0. I'll put in, let's put in t for 0 t 3 and 0 for t greater than 3.
Should the bottom one be for 1 less than or equal to t? It's not the
Yes.
bottom one, so ht, bottom of the h.
So this ends up looking like that. Let's make this just a little more fun. So, I mean, I'm going to put a 1/3 in front of that, so that becomes the height of 1 there.
That's our input.
So, what does this process of convolution look like? What is the convolution integral?
It's just the integral from like negative infinity to infinity of your impulses going through your transfer function of impulses, right? Something like that.
Next time you say transfer function, I'm going to throw something at you.
Well, okay.
I think he's bluffing.
Transfer
Bluffing.
What?
Solid bluff.
I said I think he's bluffing.
Who?
Solid bluff.
I actually. So please don't hit the computer. But, Trace may get it. Huh?
I mean,
So,
You know, generally I have an overdamped response, so.
so back to this. What is the convolution integral?
It is x of tau h of t minus tau d tau. And there's y t equals.
And H is not the transfer function. Hey.
Okay, but actually you used it correctly there, so I'm not too. H is not the transfer function.
Well,
What
why
is
the
H?
hell are we calling it H? That's confusing. Okay, fine.
So very quickly,
Fine, big H.
that's the transfer function.
Yeah, but I never use upper and lower. Okay, you got me there.
Okay, so our output to whatever input we have, whatever input, can be obtained if we convolve that input with our impulse response. For any system, as long as it adheres to two fundamental properties. What are those two fundamental properties?
Linear, time invariant.
Linear, time invariant. It's like you guys hear me say that a lot.
It's a handful of things. That's 2 of 5.
It's literally a handful. So, as long as our process is linear time invariant, I know what my output is, given any input, if I have my impulse response. How cool is that? I mean, just think about that for a moment. I have fully characterized my system with just this piece of information. Just that impulse response fully characterizes my system. So it turns out that there's two flavors of the convolution integral, and I'm just going to throw this up there. I'm not going to derive the other flavor.
Will we always use this flavor?
I don't care. It turns out they're the same. It's going to rock your world when I do this.
Is it blue? That's
Uh,
oh wow.
So it doesn't matter whether I do my flippy shifty thing over here, or I do my flippy shifty thing over here.
Calls for a wow.
All right? It's the same. So let's think about turning these things into English. If I turn one of them into English, we can turn the other one into English as well. So in English, I'm going to change my axis from t to tau. Have these axes, and I'm going to plot my h of t, which is this way. And I'm going to plot my x of t, which is this way. And this axis is t. But I don't want this axis to be t.
No.
I want this axis to be tau. I want an x of tau. right? So all I'm going to do is change my axis to tau. That's what I'm integrating over. So I'm happy. But now let's look at this piece. This piece is not quite there. I'm happy with this one, but this one I'm not quite happy with. What does this minus tau mean?
They're just shifting.
Flip it.
Flip it!
Flip
We're gonna flip it! So I'm doing this one step at a time. And we'll end with what we want up here. Right? So none of these intermediate steps sort of are mathematically making sense. But they're going to combine into something that does in the end. So I'm going to flip it, and that's going to be x is not being flipped. Start too sharp. So that's 3, that's -1, that's 1. What is my axis? Tau. Relative to my variable of integration, what is t? It's just a constant. So what does it mean when I say t minus, well, t plus the flipped thing? Let me say it that way. T plus the flipped variable. What does that t do? It just, what does that mean?
Well, it doesn't scale it, but it adds to it.
Yeah, shifts it.
Shift it, maybe.
So we flipped it, now we're going to shift it. Flip it, shift it.
Reverse it.
Shifted it.
So,
No, we flipped it. We flipped it around the axis. So.
It should be the other way.
Oh, we didn't flip it.
Yeah, you just shifted it.
Yeah, we shifted it.
It's
Yeah, you're right.
shifted.
Should it be flipped?
It's not flipped.
oh, sorry, you're right.
Okay, that makes life a lot easier.
Yeah.
Thank you for catching that. I apologize to everybody who wrote it. You should all use tablets like Stefan.
Yeah.
Or pencil. Of course, it's hard to get a lot of good colored pencils that erase well also, so if you're trying to do colors, it's...
Plus they smear. You know.
That's a classic.
Oh, hey, yours does have.
So,
Close to that.
we have to flip it. Now we're going to shift it. I'll put the input in. When I shift it, I'm going to shift it to where? Wherever t is. I don't know where t is to start with. necessarily, right? What I'm really interested in is all of t. So I'm going to put this into different places of interest so that I can figure out what my output is for all of t. I'm going to begin by conceptually putting this all the way over here. Way over. Somebody help me knock down this wall, please. Go
To the hallway.
to the hallway and
I think
through
we
the
get
hallway.
kicked out of the campus for that.
Do what?
We get kicked off the campus.
Oh, well, we're leaving the campus anyway, right? How far that way are we going? We're going forever, right? Because negative infinity, right?
But we know it's 0.
But we know it's 0.
I feel like
Don't
we
have to
narrowed
kick-
it down. Yeah.
So, in fact, it turns out that if we look at any t anytime t is less than 0, what happens when I multiply the green and the blue lines?
It amounts to 0.
It amounts to 0. So, what's the value of the green line here? What's the value of the blue line here? What's 0 times 0?
Oh, okay, I got it.
So, let's do this integration right quick. If t is less than 0, then the integral from negative infinity to infinity of let me write this way. Y of t equals the integral from negative infinity to infinity of x of tau times h of t minus tau d tau. And this is what? 0 if t is less than 0. So that's simply equal to the integral from negative infinity to infinity of 0 d tau, which is 0. We've done half the problem. Done all the negative stuff. Now I just have to worry about the non-negative stuff. What questions do you have about how I got here?
So you have that point labeled as this 2 and this 1 and t. I thought our axis was tau.
It is. So this axis right here is tau. When
Oh.
t is this value,
So it's
so when I assign some value to t that happens to be negative, I put this blue shape on the left side, right? So when tau is t, I get this value.
Okay.
This, right, I know that the length of this triangle is 1. So when tau is t minus 1, I'm just ready to ramp up. Does that answer your question?
kind of
So in English, would you be saying, looking at time t, the output is, or if you're looking at before the signal happens, the output is 0. The idea?
That is true in this case, and that is true in the case of all causal systems. Right? Remember we talked about causality as being one of the properties of systems. So let me come back and see if I can rephrase this. Would it help if I did this?
Yeah, it's not actually time.
No, it is actually time.
Well, it's not it's defined at a certain point.
Or I could take it as
It's a value for time,
that.
right?
Let me call it that.
It's
Right, so if I give you a specific variable Tn, which could be -7, could be -4.3, -6 pi, whatever, right? Would you agree that whatever it is going to be where this thing ends? And where it starts will be 1 minus that. That's it.
So, okay,
Right.
ask you, why would you put tau in there?
Why do we put tau in there? We put tau in there.
If we're going to be using time, where time will indicate that position of that value, what's the point of putting tau in there?
So the point of putting tau in there, right, if you think back to the way we were looking at the 3 boxes that we had, right? We were talking about how their effect decayed over time. And so that if I look at some time, I'm really adding up the value of this past time for this time.
Okay.
And so really what I'm doing is I'm calling tau. When I say past time, I'm giving it the symbol tau.
Okay.
And when I'm talking about the current time, or when I'm talking about like time as it really exists to us, I'm talking about t. Does that answer the question? Good question. What other questions are there about this? Who is having a hard time following?
Yeah. I'm waiting for that.
Okay, we're waiting for sort of the epiphany.
Yeah, aha moment.
Okay.
Hopefully.
Yeah, that comes when we get done with convolution.
I'm hoping, in some ways, I'm hoping there's not an aha moment. I'm hoping that I'm setting it up well enough so that it's understood as we go through it. For me, that aha moment literally did not come until over a decade later. And I looked at it and I had that.
You're already 6 foot under at that point.
The real question is one, do you understand fundamentally why we are doing this? Okay, that's the first question. If you don't understand fundamentally why we're doing it, then we don't care. 2, do you understand how we got here?
I'm just saying, like, after I was given another problem.
Okay, that's fair. Well, let's finish this, and then I'll give you another problem. How about that? So I'll take the subscript off. So now what I'm going to do is I'm going to let t start moving around. And it turns out that as long as t is negative, right, that's what this says, I'm going to get 0. But something magical happens
It's not less.
when it's not less than 0. Right, so I'm going to start dragging it slowly this way. Does somebody have a piece of paper I can borrow
Yeah.
Ideally, it would be blue.
Oh, so you basically
Got
say.
blue on it.
It's got blue on it. Okay. Oh, I can make that work.
So what you're getting at is when your output responds as your input is still being processed.
Say that again.
So your output affects your input. Now is what we're talking here. Or sorry, no, your input is your system is given an input, your impulse, but it responds right away, and the impulse affects it where it normally wouldn't.
Yeah.
No.
We'll just hold it this way.
Well, just trying to get the blue line so that it makes the triangle.
Yeah. It's not worth spending the time with. Okay, so what I'm gonna do is I now have my triangle, right? Yes, it's facing the right way. And I am going to start dragging it around. We know that it has a length of 1. The bottom edge of this is 1, right? Tell me when things get interesting. Right? They're not interesting over here. When do they get interesting?
When it reaches 0.
So they start
Okay.
resting.
They start getting interesting. Okay. So it's a little interesting, right? And it's going to stay interesting for a while, but it's going to get differently interesting.
Try and get it possible.
Different.
Not more, just different. Tell me when it becomes different.
It's different.
It's different now?
No.
So there's something in it.
Well, it was intersecting it over here too, right? When it's just a little bit positive, it's intersecting it, right? Is this different?
No.
The same equation, so as long as t is not too big, I get the sort of the same equation up here. I get the same expression inside that integral.
Okay, now it does,
Now things change.
because it's past 1. Because for h of t greater than 1, now is 0.
T is too big. It's too powerful.
For h of t.
So then as I keep dragging it this way and sort of erasing things, I guess, I enter a third realm on this end,
Where your output happens before your input, essentially.
and then a fourth realm.
So, no, I'm kind of confused, because for h of t greater than 1, I mean, shouldn't that all be 0? Or just h of t is 0?
So let's
But if
work
you're,
them out one at a time.
but h of tau is not.
Move this screen back. So if my blue now looks like this, under what conditions does my blue look like that?
When
G is
Is less than 1.
T is less than 1, but greater than 0. Okay. So, when that's the case, let me use red to write the product. Product looks something like this, and then this would be, what, something kind of like that, and then down to 0 and out. I'm not worried about quantitatively what it is, just qualitatively.
What is red?
The product of blue and green. So I guess if that's 1, this would just be a little bit more precise. It's less than 1. It would approach that value. There you go. Okay. That isn't more quantitatively, but it's still qualitative graph. Sketch. So let's do this integral now. I'm going to have y of t is equal to the integral from negative infinity to infinity of x of t minus tau, which is 0, I'm going to break this up into three pieces, to 0 of 0 d tau, plus the integral, so this first one is integrating everything over here. The second one will go from what to what? No.
0 to t.
0 to t. Right? This is t. So I'm going to go from 0 to t. And that's the equation now that I have is I have to figure out the equation of this. See, my x of t is 1/3 t. What is the equation for this line?
For which line?
That's just,
For the blue line.
yeah, 1/3 t. No,
So the
just
green one is 1/3 t.
plus t naught. So 1/3 t plus t naught.
It's what?
Wait, 1/3 t plus t of 0.
No, because
No.
1/3 T is
Tau.
green.
Is this tau?
It's tau. 1 over tau.
T plus 1.
Sorry, this should
Oh.
be, sorry, I put that to you. That should, thank you. Back to the correct domain. So the slope of this is what? 1.
Plus 1.
What is the y-intercept? How do you get 1/2?
It's not 1/2 to.
You don't
No,
know.
no.
It'd
It's t of 0.
It'd be,
Or h
What
of
is
0.
1/3?
It's h, yeah, h of 0.
It looks halfway.
it'd be 1 minus
1/3
T.
1/3.
No, or,
Right.
45-degree angle.
But it isn't 45 because the distance for
Isn't it
tau
just
is not
T?
necessarily distance. For
No,
units.
but it is, but it's,
Square root of 2 over 2?
So you're telling me that when
wait,
this,
it'd be-
Oh, no, it should be, what, 1 minus t?
So if it was, but it's not though, it's like it has
So
to
when
do, it has
t,
to,
when t is 1, the y-intercept is 0. When
Yeah.
t is 0, the
but that's not
y-intercept
though,
is 1.
because it's gotta, it
Yeah.
has to do with the angle though. Cause you have it's gotta be like a sine of 45, because it's at an angle, this position is going to be 1 minus t. But this position up here is going to have to do with 45, like a sine of 45 times that, right?
It's,
I mean,
you're saying depending upon what t is. It's your y-intercept.
it does have to do
change.
with what t is. So, I don't know, well, anyway. Okay,
He's got
because,
pens.
okay,
I think we call those markers
what's
these
fun
days.
about this, right, I'd like to just remind you that this is
No,
stuff
hey,
done in
over
grade
there.
school,
but where?
right?
To the left.
That when I
Left,
jest about
right here?
small
Yeah.
boy or small child,
Okay,
But it's moving.
You don't have
Yes.
to use any trick.
yes, this is the same angle as this, right? These are same, this is actually 1, and this is 1 total length. Okay,
Yeah,
right? So wherever t is, right, so say t is here, right? This is 0. T is the total, this is total length 1. So 1 minus t is this position. But this, right here, this height has to do with this angle, so it's,
Sine of
This
45.
yeah, right? So it's sine of like 45 times,
Square root of 2 over 2.
why would it be square root of 2 over 2?
That's sine of 45.
Or square root of 2 over 2 times
What
whatever.
a unit circle.
It's not.
But the problem is 1 on your y-axis is not necessarily the same
Why are we using
distance as 1 on your
trigonometry?
x-axis.
don't
This
think we
is,
should use-
I'm saying, this is not the same. It's this length that matters. And then times, the sine of 45 or square root 2 or 2, as you said, and that will give you this height. So you need to figure out this height based on this length and this angle, right?
So
Because this is going to be a 45 degree. This is a 45 degree. This is a 45 degree. This is a 90.
Can't we just evaluate h of t at 0?
Similar angles.
Yeah, but yeah.
It's the same triangle.
Why can't we do
Just
just
the
I
length.
know,
Because we've got
but
this
the question I had is, if
If they're the same angle, so they should be the same angle.
So,
So it should be.
Well,
it should
it's
be-
all it
what
is
if
is when
tau was
tau
an
minus
inch long
t minus tau is
and
well,
your
no, not 0.
vertical axis
let's see if we can think about
Actually,
it.
no, it would be the same as that. It'd be the same as what's left over. So t minus 1, because it's a 45 and 45. These angles are always the same.
You mean
These
1
lengths are always the
minus
same.
t.
What's that?
You mean 1 minus t. Right.
Yeah, whatever.
And t equals to 0.
Yeah, 1 minus,
one
1
minus
minus
t.
t.
Because t is, whatever. So whatever's left over, it's the same. So you could do it sine, but it's the same because it's a 45 degree angle.
So basically, the answer is 1 minus t. That's been set. Just so.
Yeah, no, I was waiting for consensus.
Oh.
Well, generally, I don't think it's a good idea to like use like trigonometry on this stuff. Because you change your function, you change your trig. I mean code.
But the thing is, if it wasn't a 45 degree,
You
you would
will,
have.
so you will need to use whatever math you need to use in order to figure this out. Right? So, I mean, in this case, I made these sort of triangles. There's no reason they're not sinusoids, decaying sinusoids. There's no reason they're not decaying exponentials or rectangles or whatever shape I decide to draw. Okay, so we decided that this point right here is what?
1 minus t.
1 minus t. Right? So if I put this into slope-intercept form, I have my h of t minus tau is equal to what? My slope is 1 tau, plus 1 minus t. Right? What questions do you have about getting this?
So your t is 1 tau. That's what's good.
My slope here is 1, which is from the definition that I have way back in the day. And so then my intercept, what's left is figuring out my intercept. So I am now going to put that.
So 1 tau plus.
Yeah, that's 1 tau. So I'm simply going to put that into this, and I'm going to get tau plus 1 minus t d tau. Plus a third integral. What's the third integral? T to infinity.
Oh yeah, that's sorry.
T to infinity of 0, right? The product above that is 0. D tau. I'll do 2/3 of this problem.
Yeah.
Well, you guys do this middle third.
Mr. Helper.
I like to do my fair share of the weight, right? I like to carry it along with the rest of you. So take a moment and integrate this.
I can use it now, then after a bit.
You mean they've invented them?
One third L squared.
Next time you can do it.
Minus. He's doing that. No, he's doing the same one.
Forgot T squared.
For
It's
child.
6 T squared.
Is that the same as my
Not the same.
Where do you get the stuff?
What, I didn't get it, Bob got it, but, minus T squared,
Times T minus 3 over 18.
yep. But I don't think that's right.
I think it is, it's just simplified.
I don't know if that's simplified.
Expand the top here.
How did you get, where's your tau's, tau equals 0? Two tau.
So then I'll combine these, so that's where I'm gonna end up with my 18, right? So I'll end up with 2 over 18 TQ minus 3 over 18 TQ plus 1/6 T squared.
Well, they did the same thing, they did,
Which ends up being
3 over,
negative 1/18 TQ plus 1/6 T squared.
they combined theirs.
They combine those.
So they combine it all into all of it over 18. So then they factor out
Oh.
T squared negative and then T minus 3.
So really, this is simplified.
You can go one more step. Perhaps.
Coming to the denominator, 18.
They
In terms of just getting it to a basic
Yeah.
polynomial.
Yeah.
Not a basic polynomial.
How do we use these
I have one.
polynomials?
I don't know.
All right.
Yeah, that's good.
So I'd like now you to take a turn doing this. So this is if
T is greater than 0.
0, T,
Equals
and 1, right? What is the next interesting range that we have? Next interesting range that we have
T greater
is when t is greater than
0.
0 but less than
3.
Sorry, when t is greater than 1 but less than 3. Right? At that point, the blue triangle is all the way in the green triangle, but hasn't yet started to leave. You do that one.
We have to look on the test, we're just gonna have one problem.
The blue triangle is where? Above 0?
So, right,
In
so
between-
the
in
blue
between T and
triangle
tau.
would be all the way, all of it is all above 0, which means t is greater than 1. Right?
But less than tau.
But less than leaving the green one.
3.
It would leave the green one when t is greater than 3. So I am between 1 and 3.
So it could be equal to 1.
Yeah, well, so I would put equal to 1. I tend to put, I mean, technically these
I
can
would just-
matter
I would
to
change that
mathematicians.
to, from 0 to 1 and then from
The same
less
thing.
than 3. Right, I mean, otherwise you're not including 1.
I was thinking.
So I would do, the next one would be if
T is,
1, t.
yeah, that's what I was saying. That's exactly what I said.
And then the last one would be.
Because otherwise you weren't including 1.
No, so yeah, so I was thinking the same thing. That
And in some ways, those are details mathematicians care about, and engineers don't, but mathematics is the language of engineering, so we shouldn't be too down on it. And the red part, then will look like that.
The red part is what we're talking about.
The red part is the product, right? The red part is the integrand. Right, that's what the integral is operating on. So the first step, right? What is the equation for this shaped name?
Blue.
No, it's
Right? If I sort of, I know that it's 0 everywhere else, but if I sort of extend this out, I should be able to get an equation for that blue line, right? And then I know I'm still just going to have 3 parts to my integral. I'm going to have the left part where it's all 0. I have the right part where it's all 0. I'm going to have the middle part where it's interesting.
So the one with the T above the top.
Still the same. It's just the same. Second one.
Did you guys get t times t minus 1? You get t times t minus 1? Oh, you get it.
You're doing what?
That equation.
No.
T times t minus
Where is the red? Oh, 0.
Where's a red curve not 0 at the intercept t minus 1?
So the red curve is 0 all the way up to
T minus 1 times.
That's
t minus 1 to t. Because you're going to be integrating where it's not 0, right? Right. Really, we're doing the whole damn thing. It just so happens that I'm willing to do 2/3 of it for you. Right?
But it's, so that closure is from t minus 1 to t.
Correct.
We have to use like some super basic algebra if we're going to intercept it.
Yeah, so it's like how you define a linear line. So now we no longer have a y-intercept, we now have an x-intercept. So y equals 0 when x equals t
I
minus
mean, you can
1.
still draw the dotted line and put that x, put the y-intercept there.
Oh, that's stupid. Well, that would be. Well, yeah, it does.
Just draw it out.
Well, actually, wait, if you draw the intercept.
It's gonna
Yeah.
be y equals x shifted.
T minus 1.
E plus 1.
T minus 1. You said
I feel like it's a super
1
simple
minus
solution.
t?
I had t times t minus 1. No. No, that wouldn't do it. Eh.
When this was, let me ask the following.
Whoops.
Slope didn't change.
When this was over here, we calculated our intercept, right? Anyway, and if we slide this around, nothing changes that intercept, right? If just because it happens to slide further this way, does that actually change the intercept?
No.
So it's the same thing.
Not when it already depends on that variable t.
The slope is still the same.
Right? The slope is still, everything is still the same. The only thing that I've changed is t, and t is part of my equation. So really, the only thing I have to do here is update this to be and then this part will change. And now this is for t between 1 and 3. What questions do you have about that? Was there anything people don't understand? What don't people understand?
So, is it fair to say that in all cases it's just going to be our actual line? So in this case, what would be if that was x squared plus 4x minus 3, and just add that to power?
Well, I happen to pick a nice convenient line over here. But there's nothing that says I have to pick a nice convenient line, right? I mean, if you design your system and it does not have this impulse response, right? You have to use the impulse response of your system.
So how would you do it if you had a super complex one? So you just basically added tau plus our line. Is that what you would do?
So the question is, what
do it by hand.
What happens if this is super complex?
You outsource it to India.
That's a really good question. And it turns out that I don't do it this way. This is why, right? So I hope we all agree now that this is brutal.
Yeah.
Like, who's going to wake up tomorrow morning and think, hell yeah, I'm going to do me some convolution? Well, yeah, but that doesn't mean you couldn't do some tomorrow. I mean, just for fun, right? I mean, like, my gosh, I'll bet if we could charge people for this, right? Get them to line up and like make it like a carnival ride.
I feel like you're mocking us because we paid to go here. You've already gotten people to pay for this. Thank you.
Well played, good sir. Well played. But it turns out that this is not very much fun, is it?
Nope.
It turns out that this is really hard and takes a long time and is painful.
That's why transfer functions were invented.
Yes.
Fun.
That's why we're going to move from this pain in the ass time domain into the frequency domain. We're going to keep doing the same process.
Oh.
We're going to tear signals apart. We're going to put them through our system, and we're going to put them back together. But we're not going to do it in time. We're going to do it in frequency. And when we do it in frequency, this whole mess, all of this, you know what it comes out to be? Multiplication. Done.
A lot of times.
So you beat us up with this, so we'll embrace the other way, or the other way.
That's part of it, but more importantly, if we do this, right, I'm really working on selling you the value of this.
Does this mean we all get to?
I want you, do what? Okay. I want you to buy into this. And I want you to buy into this, right? I mean, they're the same thing.
Well,
I want you to believe in it. I want you to have played with it enough that you see it works. If you believe this, if you believe this, we can take the next step. But if you don't believe this, then there's no reason to move on.
So what if I'm trying to use the next step to understand this step?
Right?
But that doesn't. Yeah.
I mean, this is fundamental. It's not fun. Not cool.
I was thinking the same thing.
Right?
It's not fun.
But it is.
That's fun.
It is just, if you get this, right? Here's the cool thing. Watch where we're going to go. I'm going to take my tau, and I'm going to break it up into exponentials. Now, how do exponentials relate to integrals?
They're the same thing.
They're eigenfunctions! They are eigenfunctions of integrals. So if I put an exponential here, and I do the integral, I get the exponential just stays.
Yeah.
Done. That's the cool part about it. But I can't do that until I get this. So, I want you to finish this. For next time, go ahead and finish this whole convolution process. We'll make that homework 1.
So we're going to.
So finish
the
convolution for this property. Right? We're sort of
We go from
a third of the way done with it. We've got a couple more steps to go. Right? You can finish this integral. And then there's one more as we move this, start moving this out. And then there's one more when it's all the way out. What questions do you have?
Wait, there's only the only one would. Oh, so you're gonna have
tau
one where.
It'd be t greater than 3 but less than 4,
Yes.
and then t greater than 4 to infinity.
What questions do you have about what I'm asking? I have now even run out of my time and run over my time and ignored it a little longer. So we should all probably
Nobody walked out.
Unless you wanna hang out and get more
That should be
time.
good. Right?
Which I will.
People walk out.
do.
Maybe next week.
Hey, either want